Howdy. Glad to see a crowd here. Chris, Sachin, Luai, Hannah, Samira, Rhea. Cool. Oh. Hi, Lorelai. So are we doing a food thing on Friday? Is that what we said? The day before break? Oh, hi, Justine. So food party on Friday? Is that correct? No, I don't remember. Is that what we said, right? Thursday? Thursday. Sorry, Thursday, 10:37. Yes, Thursday is correct. I misread the schedule. Sorry. So next Thursday we'll have this Thursday in 3 days we'll have the food day. We're doing it during our scheduled slot, which is 10:37 to 11:22. Okay, good. All righty. So, hello. I'm glad you guys are here. I have, I think, a pretty cool problem to look at today with you guys. I also have some cool new equipment that came in. So I got some new pens, actually, 2 different packs. So, yeah. So, yay. Hopefully those colors work out better for us. And I also have gotten another board to hang on top of our board, which is kind of snazzy. I hope you like that. So we can work on here, and my plan is to then do graphs on here. We don't have a graph today, but for graphs, I'll have a grid on here, and then we can use it for when we have to make a graph. We'll have it kind of as a pre-made apple pie in the stove, where we can pull out the grid rather than make up the grid ourselves during the class, which is always a little bit sketchy. Get it? It's sketchy. So the graph will be a little more precise. But today we'll just use it as to get started on our work. And then when we want to move on, I'll just move the board and then we can move to the space underneath. Wow, good. Okay, so we're working on the 2014 free response. And I did WhatsApp it to you. WhatsApp it to you, and here it is. If you haven't seen it yet, it's kind of hard to see. It's basically a scientist's model for what the hydrogen atom looks like. And we have a nucleus consisting just of proton. Well, hang on a second. They don't say proton. So it's electrically neutral with a charge Q. Fine. Okay. So our idea is this. And I'll just sketch it. They give you the equation here, and I'll write down the equation first of all. So we have 2 densities on top of each other. So we have rho of r is equal to, okay, this is for the electron. So this is for the electron. We have, oh, interesting. Ha! Creative. Okay. So we have minus beta over r squared e to the minus r divided by alpha. Okay. And this is for, oh, sorry. A, not alpha. Oh man, my hand is hard to read. No, that's alpha. Is that alpha? It looks like alpha. It is alpha. Well, that's baloney. That's not true. Okay. I don't like the question, the way it's formulated. Okay, anyway. This is for r is smaller than alpha. And then for r greater than alpha, they're going to say that the electron density is 0. Yeah, it is alpha. The reason I got confused is because that's kind of showing up weird on here, isn't it? Is that showing up weird? All right. Well, that's showing up okay. The reason I got confused is because they're saying alpha and beta are positive constants. Okay. Well, that really sounds like they're just numbers, but they're not numbers. They are specifically, they have units, okay? And alpha specifically has the unit of length, of course, because it's here in the exponent r divided by alpha for that to work out. So, and then we have for our nucleus, okay, we have just a point charge at r equals 0, okay, and nothing beyond that. So we just have a point charge for our positive particle, our nucleus, and the electron around it is kind of like an electron smear, like a distributed electron cloud where the electron charge is distributed through space, but they let it stop at some point. Whereas in reality, and kind of the way I describe it, this electron distribution really goes on to infinity and beyond, but they cut it off at alpha. There you go. Okay, so here's the basic idea, and they're asking us to use these two, the nucleus and the electron cloud, to think about Gaussian surfaces. Okay, so the question is, for the nucleus, if we apply a Gaussian surface around that, that's going to be pretty straightforward. So we've got our space here, and being all nerdy, we've got our x-axis, y-axis here, and our z-axis there. And here's our Gaussian surface. Okay, and we have our charge. It's a nucleus at the center that is just there. So all our charge is concentrated at the center. Okay, I can't even draw it obviously as a dot. This is our positive charge. And no matter what radius we choose, all the charge will be inside it because it's a point charge. Okay, now we know point charges don't actually, okay, for a nucleus, the nucleus has actual size. So that's crap. But they're telling us it's a point charge, like a real point charge, like no size at all. Nucleus actually has size, but we're going to ignore that. And whatever radius we choose, it will always contain all of the charge. Okay, so for a graph as to how much charge is included for our Gaussian for the positive charge, no matter what radius we choose, we're going to get all of the charge included. This is for our nucleus. Oops, yep, correct. And then here we have alpha. Okay, good. So that makes sense so far? Okay, yes? Okay, pretty straightforward, I hope. Now, in terms of what's going on here regarding our negative charge, our electron cloud will eventually have as much charge in total, okay? And we know that no charge is beyond alpha. So we know when we get to that point of the radius. Oh, the screen isn't really showing up great. These German pens are really not as good as Expo pens, but I couldn't get Expo pens on Amazon in a reasonable time. I'm going to use purple, maybe the purple works better. Let's try that. So here we go. That's the nucleus. Yeah, that's nice fat. So once we reach that radius of alpha, we should have all the charge. And at the center, obviously, we have no charge inside that point. Okay? And of course, this needs to be an exponential asymptote, kind of, but meets that point. There we go. And then after that point, it should keep going. For a larger radius. Okay, so this is for the electron cloud. And this is for the nucleus. Okay, makes sense so far? I hope it does. That's part A1 and A2. So here's A1. And this is A2, not AII. There you go, A2 down here. Okay, so we've got that so far. And now we're going to move on to question B. So, okay. All good? All right, so now we're going to just take this and remove it, and we got a fresh board. Hey, that's pretty cool, right? Yeah, I thought that was pretty nifty. Okay, good. Okay, so we're now on the second page. Why is there a blizzard outside? You guys are so funny. Blizzard, you're cute. I lived in northern Wisconsin for 3 years. This is nice weather for September there. Okay, all right, so part B. So part B asks, the dashed curve on the graph below represents the electric field as a function of distance r due to the positive nucleus of the atom without any electrons. Well, hello. I mean, we can figure this out ourselves, and they tell us this. Fine. Okay, and of course that's true because the electric field versus r, okay, and here's alpha. Okay, of course looks like that because it's a point charge. Okay, it's a point charge at the center, and the electric field of a point charge is, of course, just K, this is plus Q, divided by R squared. There we go. That's all it is. No surprises there. So, on the same graph, sketch the electric field as a function of distance R for the neutral atom as defined by the scientist's model, which includes the nucleus and the negative electrons surrounding it. Okay, so I kind of switched colors on you here, didn't I? So purple, this is now for the proton. Maybe I should switch back to the red for this, and that's not going to be weird, but I'm going to do it. Okay, so this is the proton, because we had it positive here. There we go. And this is for the positive object. Okay, and now we're going to think about what the negative object is. Oopsie daisy. We're going to do not the negative, but the total. And for total, we'll use black. There we go. So we use E total. Okay, now let's just think about that for a second. Good one, Justine. That's true. That's true. Yeah. Don't go outside because the weather is scary. Good. So if we look at the total electric field, so now our model is, and we'll just draw a picture of what's actually going on. We had that just a second ago. We've got the central charge, right? And then we have around it, and this goes out to a radius alpha, kind of an electron cloud, which is the negative charge right there. Okay, so once we hit alpha, right, beyond alpha, right, this thing is neutral looking inward. And if it's neutral looking inward, of course, how much total electric field should we have beyond alpha? This is the participatory part. Electric field beyond alpha is 0, 0. Good, exactly. So electric field drops off to 0. And if you want to get all hyper nerdy on this whole thing and say, I'm going to drop in a Gaussian surface and all that stuff, you put in a Gaussian surface on this alpha radius sphere. Inside we have 0 charge. And of course, Gauss's law says E dA integrated equals Q inside divided by epsilon naught. So if we integrate over that surface at radius alpha or any larger radius, then inside that radius we will have zero charge, zero net charge, and therefore it should be right there. All right, good. Makes sense. What that also means is that to get to zero at this point, that means we need to have a negative electric field at that point that cancels out the electric field from the positive one, right? Makes sense? So at that radius, it's the same value. So whatever value we have up here, we have, whoopsie, we have down here a negative electric field. This is the electric field from the negative. Okay, at that point it's negative. Okay, now we also know that the electric field at the center, right, is zero. Okay, because inside the electric from the charges, because at that point we have no. Wait a minute, is that true actually? I think so. So it's got to go to zero to get here, the total, but the electric field at the center is actually zero, but we have no radius. And the electric field, I'm thinking about this too much. We're just going to sketch it. Okay. The idea being that here, initially, the charge inside it, the negative charge inside is very small or none. So it's very close to this one, and then it kind of separates. And then meets that line. So that should be our total electric field. There we go, E total. That makes sense to me. Okay. Okay, does that make sense? I hope that makes sense. I got myself a little bit confused. I don't think it should be right touching there because it's going to touch it at zero, but it never gets to zero because it blows up at zero. So we're just going to not go there. Okay, that makes sense for the sketch of the electric field? All right. Okay, part C. We're now asking for us to derive the expression for the electric field strength due to the neutral atom for the following positions in terms of Q alpha, beta, R, and fundamental constants as appropriate. Okay. Oh, well, that's stupid. What are they doing here? Okay. So now we have to watch out because they're hateful people, these physics graders. So we have now asking to find E for two things. And we're asked to find E specifically for R greater alpha. And they were supposed to find it for R smaller than alpha. Now, watch out. Here's the problem. You might be tempted to just do this. E is equal to 0 for R is greater than alpha. Well, that is indeed correct. However, that earns you 1 of 3 points. Ow. And the reason that's a problem is because of the word derive. And by derive, we do not mean take a derivative. We mean start with an equation and then manipulate that equation to come to a result. So even though we know that the electric field outside the radius of alpha is zero, we need to actually show that. So to show that, we have to start with an equation, and they tell us what equation to start with. They say start with Gauss's law, derive from Gauss's law. So we got to restate Gauss's law. E dA, there we go, equals Q inside divided by epsilon zero. There's Gauss's law, clearly stated. We can do a little thingamajigger here for the area integral or something like that to make clear what we're doing there. Now we need to say that Q inside is equal to zero. Okay, because the electron cloud has as much charge magnitude-wise as the nucleus. So that means that the integral of E dA is equal to zero. And that means that the electric field is equal to zero. And now we have gotten our full points. So now we're at 3 out of 3. Okay, even though this seemed maybe like a straightforward problem, I hope you took something away from that part in terms of how to deal with this kind of problem. The screen looks a little dark. I'm going to see if I can get a little bit more light in this room because, yeah. Oh, we got some kind of light bulb now. Okay, good. Nachricht zurückgezogen. Okay, all right. Alrighty. So we've got a little dot there, but I think we're okay. So there we go. Good. So that brings us to the second part. That was C1. We got that correct. Now it's time for us to take a look at C2. And for C2, let me take a picture of this, and then we'll move on. Okay. For C2, we're going to have to find what happens inside the nucleus, and that, of course, is the crunchy part. So C2 asks for specifically for R is smaller than alpha. Okay, so for that, we are going to need to find how much charge is actually inside, because to find the electric field, E dA is going to be equal to Qn divided by epsilon naught. Okay, and if we think about that situation, here's our big electron cloud. Here's our center. This is positive. This is alpha. This is our negative charge. Now we're looking at some radius that is smaller, r. Okay, and now we know that the charge inside this black Gaussian surface, the Qn is greater than zero or smaller than zero, positive or negative. What is that charge? Positive. Okay. Positive is correct. Okay, I need some feedback here. Is this like okay, or is this too challenging, or is this just about right? Is it boring? Too hard. Too easy. Just right. Too hard. Too easy. Just right. It's okay? Are we doing okay? You sure? Are you guys sure? It's good? Just right. Okay, good. Is everybody else of this same opinion, or have we tuned out? Okay, good. All right, I'm just going to keep going. It's a positive charge inside. Okay, so it's a positive charge in here, but how much charge is inside? Okay, that's equal to, of course, plus Q, that's the positive charge, minus the negative charge. The negative charge. Okay, the negative charge is something that we need to figure out by integrating the charge density. Okay, they give us the charge density. And if we integrate the charge density over the volume of that sphere, then that's going to be the total negative charge. Okay? Make sense so far? Okay, so integral 0 to r. Okay, now at any point, the volume, any kind of the amount of charge that is in any kind of volume here is inside this. Oh God. Okay, let's see. Okay, this sphere, it's kind of okay. Good, good. Thank you. I kind of felt like I lost you. We're going to bring on our second board and kind of do a little side view of that to kind of figure that out. So here's a quick reminder on how we got started in the beginning of the problem. We said that the charge density for the negative charge increases. Is this charge density right here? It doesn't increase, but it changes. And it also said that we figured out that the negative charge eventually is the same value as the nucleus charge. Okay, it's eventually by magnitude the same value, but initially it's none because in the center there's no volume at all. So let's take a look at how we could actually find this value for how much charge there is at a specific radius. If we do that, I'm just looking at this, okay, for that part. So we're saying up to a certain radius r, we'd like to know how much charge is inside this radius. So to get that, we have to be like, okay, we're going to integrate r from this point, and here, of course, r is 0, and here r is r. That makes sense. And we have to think about this ball of charge like an onion. So they're basically different skins of onion all the way out, and each layer of skin has a certain amount of charge because the density of the charge is not constant. It varies, but it's constant for a certain radius. So for example, if we look at this radius right here, at this radius, we have a certain onion skin, and it's very, very thin, very, very thin. It's actually no width at all. We can make it as small as we want to. It's a differential width. So this width right here, we would call dr. That's the width of that thing. The width is dr. Okay? The width is dr, and of course the volume of this skin, okay, that would be dv, and dv would be the surface area times dr, 4 pi r squared times dr is this surface times its width, which is the total differential volume of that onion skin. Shrek? Sachin? Okay, makes sense? Okay, yes? Makes sense? The movie. Okay, I don't get it. Okay, that is the... Makes sense? Ogres have layers like onions. They do? Oh, is it a metaphor? Or do they literally have layers? Okay, so this is the volume of this thing, and of course that means that the charge of this thing will be that times the density at that point. Okay, the differential charge in this red area will be the density, the charge density at that point, radius, times dv. Okay? Layers of emotion. Aw, that's beautiful. Okay, so let's remove this thingamajigger. That was actually kind of helpful. And now we come back over here, and we can see that, oh, okay, we're back to this point where we are doing the rho dv, and we're integrating from 0 to r, and now we can write in the value we had for r, rho, okay, which is minus, oh, I meant to grab the black one. Here we go. Where's the black one? Here we go. Integral 0 to r minus beta over r squared e to the minus r over alpha. Okay, now comes the dv. And dv we just said is 4 pi r squared dr. Maybe if I move out of the picture, just focus in on here. Hey, focus here. Okay, does that show up okay? Okay, now, as you notice, they designed the function nicely because they have r squareds cancel out, because otherwise we can't deal with this with our limited integration tools. So the r squareds cancel, and this will be integrable by us. It's integrable either way in general, but for us. So let's take a look. And we're going to pull the constants up front. So we have minus 4 pi, we have a beta. And then we have the integral 0 to r e to the minus r over alpha dr. Okay? Okay, good. So this integral is relatively straightforward for you guys. Okay, just a reminder that the integral of the exponential is the exponential itself. So we just have to worry about the internal derivative, antiderivative, in order to make this work. Maybe write that over here. Kind of room. So we have minus 4 pi beta. Okay, and then here comes the integral. We'll write it like this. E to the minus R alpha. Okay, so if we were to take the derivative of this, right, the minus 1 over alpha would pop out front. So we need to put minus alpha in the front in order to cancel that out when we take that derivative. Okay, so this is the correct integral. It doesn't show up pretty, does it? The zero kind of creeping down. There we go. Put this R there. There we go. And now 0 down here and R up there. Okay, now here you have to watch out, and this is really important for you guys because you tend to screw this up. When we do other integrals of polynomials, oftentimes when we plug in 0, right, that just gives us 0. So you're just tempted to just plug in the top value and boom, we're done. And then forget about the bottom value that you have to subtract. But when you plug in 0 into an exponential, it's not at all 0. It actually is a number. And in this case, because of the shape of this thing, it's actually bigger than, anyway, so we got to plug it in. All right, so let's do that. Minus 4 pi beta. Now we plug in R. Oh, and the alpha should pop out as well. So we get 4 pi alpha beta. The minus alpha pops out. And then in here we have e to the minus R divided by alpha minus 1. Right? Because when you plug in 0, you get 1. Okay, you guys cool with that? Okay. So, coolio. Okay, good. So let's aim down like this one, and then we can say, okay, well, this is the negative charge. Okay, so the positive charge, well, actually, it's just this plus the positive charge. Okay, so Q total at some radius R is equal to plus Q plus this mess, 4 pi alpha beta e to the minus R over alpha minus 1. Good. And this is the Q inside, which we're going to have to use for Gauss's law. Remember, Gauss's law? That's how we got started over here. We wanted to know the electric field. So if that's the interior electric charge, well, then the electric field is just this whole thing divided by epsilon naught. Oh, shit. No, that's what? Hang on. That's the electric. Oh, hang on. So wait a minute. Stop. Too quick. That's the inside electric charge. Oh. Okay. Everybody okay? All right. So we have our inside charge. That's this value right there. And then the electric field is, of course, constant. So it's E times 4 pi R squared. Okay. So E times 4 pi R squared equals Q inside divided by epsilon naught. And that, of course, means that E, I'm just going to do it this way. E is equal to Q in, which is this mess here, divided by 4 pi r squared epsilon 0. And this is this. Whoop. Oh, cool. Question with a minus sign. So I was a little bit sloppy when I had this thing going over here, because when I said this up here, this is where Hannah's confusion comes in. So the total inside charge is the positive charge plus the negative charge, or minus the magnitude of the negative charge. Okay, so when we figured out the negative charge, we got all this stuff here. We ended up with this expression, and this expression is negative. It doesn't look necessarily negative, but because this thing right here is a declining exponential with an intersection of 1. So at 0 r, this is 1, and it's smaller for r getting bigger than 0. That means that this number is definitely smaller than 1 for r greater 0. So this minus 1 is a negative number. So this is the negative charge. So that's why I was kind of being a little sloppy right here with this. I changed it. I kind of snuck that through there to by you. But yes, so I hope that explains why it's not minus that. Did I screw it up? I hope I didn't screw it up. Let me see. Oh, they have it flipped here. So they've got it flipped in here, and then they have a minus sign on the solution sheet. Okay, so they have a minus sign here, but they have this flipped. Either way is fine. Okay, Rhea, Hannah? Everybody okay? Okay, good. Now, I don't really like question D. It's kind of silly. What's the physical meaning of the constant alpha? So they say here as their solution, for correctly stating or implying that alpha is the radius of the atom or the radius of the electron cloud. I've talked to you guys in the context of AP Physics 2, for those of you who are back. This year, I've also talked, but the problem is that the electron cloud has no specific radius. When you guys see that picture of the 1s orbital, it just refers to a certain percentage of probability that the electron can be found if it is localized by like grabbing it at that point. 68%, 99%. It's like 1 sigma, 2 sigma, 3 sigma, whatever. But there is a non-zero probability that the electron is anywhere until an infinite radius. So it doesn't really make sense to say atomic radius. That's something we kind of casually say. So in the model, that's the limitation beyond which the atom acts neutrally. Let's put it that way. Maybe that's a good formulation. But the model is kind of goofy because they make it force it to go to 0 at alpha when actually the electron cloud does not go to 0 ever. Okay. Hey, that's exactly 3 o'clock. Wow. Okay. So I will take pictures of that board and the other board and this board. I hope it makes sense. It's a little of a tricky problem to say the least. There are 2 integrals in it. You got to integrate to find the chart. The other integral is really straightforward. There is a real integral in there, right? Because you have to integrate to find the charge, and that's sneaky. And then you have to apply Gauss's law. But yeah, they do accept atomic radius. Now, I'm not really too happy with the question. I think it's kind of goofy. But what they said was they want the statement or implication that it's the radius of the atom or the radius of the electron cloud. I don't think it's super scientific, but I mean, I don't know. I'm going to get all nerdified by this. I'm going to, as you notice. So, but that's how they formulate it. So I think it's okay. Okay, so I hope that helped you along. I posted for you guys the times for AP Physics 1. Josh Beck and Greg Jacobs are doing those. Greg, I worked with Greg this summer, past summer on grading the AP1 exam, and he wrote the AP1 book. the study book. He's very high energy and a good physicist, a good physics teacher. And the same is true of Josh Beck. Also, he actually is a good buddy. Greg is not my buddy, but I work with them. But Josh is my good buddy, and they're both good people, and they do good work. And I hope that either now or later, I think sometimes seeing something live can be more motivational, and or you can see the questions coming in and all that stuff. But also, you could come back to those videos when you start studying for mechanics, the mechanics AP exam, because they're talking about rotational motion, torque, and those kind of things in the YouTube live streams on the AP Physics 1 channel. The AP Physics C channels on the College Board should be switching over to topics that are relevant to the exam shortly, I hope. And then I'll also keep alerting you to those. By the way, the topics that are not being covered on the exam, neither our clausur nor our AP exams, because they've been cut off the exam because of Corona. We will get back to those after the AP exams and still do those topics. So I do want you guys to get the content of the class, but that'll be post-AP exam. And then we'll cover those units, like unit 5 we didn't finish for AP Physics C, E&M. That's really what we're going to do. And if we finish, that's the only one we haven't finished. So we finish that unit 5, after the AP exam. And after that, we'll do something else. But hey, no worries about that right now, because we're still preparing for the clausur and we're preparing for the AP exams. The Unit D quiz counts, yes. We'll figure something out. It will not be recovered on the clausur. So units 4 and 5 will have some impact on your second semester grade, but don't worry about that right now. We're focused on preparing for the AP Physics C exams, and the AP Physics C E&M exam will cover units 1 through 3, and therefore the clausur will cover units 1 through 3, and it will be a prep for the APC exam. Do not do those assignments for Unit 5 right now. We are in full review mode for units 1 through 3 on the AP Physics C E&M exam. So 1 through 3 only review those until the clausur, until the AP Physics C E&M clausur. And after the clausur, we'll review for C mechanics. Okay? Alrighty. So that's it for today. We see each other again tomorrow at 11:30. I will, as usual, save this on YouTube. So if somebody wasn't here, they can view it. And otherwise, stay well, and I'll see you guys later.